Alright, welcome to today's video in Unit 6 about energy, where we're investigating collisions. So we talked about collisions a lot in conservation of momentum, but now we've been talking about conservation of energy, and we want to see how that applies to collisions. So in this situation, we're wondering about, well, we know momentum's conserved, energy. Energy is always conserved, but it's all types of energy are conserved, so it's difficult to track all the different types of energy. So specifically, we want to look at kinetic energy, and that's what we're going to go through some examples to see the results. So we've got the situation here. We're going to calculate the total kinetic energy before and the total kinetic energy after in 3 different examples to see whether anything is true or not. So we've got ball A with a mass of 0.5 kilograms moving at 5 meters per second, and ball B has a mass of 1.5 kilograms moving at -1 meters per second. So they're moving away from each other, so they're moving in opposite directions to each other, but they collide. And then ball A is moving -4 meters per second, and ball B is moving 2 meters per second in this example. So what we have to do is calculate the total kinetic energy beforehand. So EK, which we have to do as EKA plus EKB, which is just going to be 1/2 MA times VA squared. So we're just trying to calculate the total kinetic energy beforehand so that we can compare it to the total kinetic energy after. So we're just going to sub everything in here. We get don't forget to square the velocity. It's going to be easy to forget that doing all these calculations. And okay. And if you calculate that, you will actually end up with a nice, convenient, completely unplanned round answer of 7.0 joules. Okay. Now, what about the kinetic energy after? So we're going to take the same approach, but we're going to use the after. So the primes, which will look like this. So again, very similar. We're just using the prime, our after velocities of -4 and 2 in this situation. And you're going to calculate that out same way. And you actually will get that EK prime is exactly 7 joules as well. So apparently in this situation, there is something being conserved. So let's take a look at the next example. So these next ones are already done for us. Example B, the same situation to start, but the afterwards, ball A and ball B stick together. So if we remember, that's an inelastic collision. And we get 7 joules at the beginning, but only 0.25 joules at the end. So that's, well, not good for our ideas of conservation of kinetic energy in a collision. And example C, again, so they collide, this time just resulting in different velocities afterwards. One's at -1.75 and the other's at 1.25. And 7 joules to start, but only 1.9 joules to finish. So again, kinetic energy conservation doesn't seem to be holding true all the time, which isn't good. We need to be able to think about it in a situation. So this is where the types of collisions come into play. So we learned about 3 different types of collisions: an elastic collision, an inelastic collision, and a partially inelastic, so something in between those 2 extremes. Now, in terms of kinetic energy, so kinetic energy was not conserved in example B and example C. So that's the first thing. Then we've got example A, which kinetic energy was conserved. And we need to know what type of collisions these are. So this one is easy. This is the inelastic because they stick together. So inelastic, not conserved, can't use kinetic energy to solve the problem. And example A, there's no way for us to know at this point, but this is actually going to be an elastic collision. And example C is partially, so the in-between. So elastic collisions, and this is the big thing here, elastic collisions, kinetic energy is conserved. And so that's how we can differentiate between an elastic collision and a partially inelastic collision or a completely inelastic collision, something we couldn't do before with conservation of momentum. So let's take a look at this example and see how we can use this to solve it. So we've got object A sliding at 3.2 meters per second, hits object B, that's 2 kilograms. They collide, move off in equal but opposite speeds. And if object A has a mass of 0.67 kilograms, what are the final velocities of the object? So you'll notice here that this is slightly different from your version of the notes, but just, again, we're solving this problem and because the other one is just far too math complicated for a good example. So what are the final velocities? We've got our givens, but it's important to notice the VA equals negative VB prime. So VA prime equals negative VB prime. That's how we can simplify our equation because of the equal and opposites speeds in the after situation. We don't know either, but we do know they're the same value, but one is negative compared to the other one. So that's how we can use that information. So EKA, because we have to have our total kinetic energy is equal to our total final because it's an elastic collision. Only elastic collisions we can do this. So now we got to simplify our equation. So the initial mass B was at rest, so this goes to 0. The 1/2 is going to cancel out of each term, and we can substitute in for VB prime. So we end up with an expression that looks like this: plus MB times negative VA prime, which is all squared. Now, if you're obviously a squaring the negative means it's not going to make a difference, so we actually just end up with VA prime squared that we can factor out of this equation, and we get MA plus MB. And so VA prime squared is equal to MA VA squared over MA plus MB. And if we square root that, VA prime is going to be plus or minus the square root of MA VA squared over MA plus MB. Put that in your calculator and you are going to get an answer of 1.6. So you're going to get plus or minus 1.6 meters per second. Looks like we've got our answers, but we just need to know whether VA prime is positive or VB prime is positive. Now if you're thinking about, imagine there being two marbles. One marble's the one that's moving is in the positive direction, so if it's going to hit another one, the only way that that marble can actually move is continuing on in the positive direction. So B has to be positive, which means that VA prime had to rebound off of the collision with a negative velocity. So those are the two complete final answers for that one. So there's 4 questions there, plus a challenge problem. Again, slightly different from your notes, so make those slight changes. And try those before you come to class. And as always, physics is awesome.